Good afternoon and welcome, everyone. My name is Sonia DeBulio, and I'm the Director of Alumni Relations for the Faculty of Applied Science and Engineering. I want to thank each of you for being here today and joining us for this special Lunch and Learn presentation. We have alumni tuning in from all over the world. In fact, from your registration numbers, 6 different countries, including Canada, England, Hong Kong, Ireland, the US, and Uruguay. I wonder if our Uruguayan guest is on the line yet. I haven't seen anybody yet from there. For those of you that are new to the Lunch and Learn, not sure if you knew, but the Lunch and Learn was founded by the class of 1935. After they graduated, it was tough times finding jobs. So the group of alumni from the class of 35 that I had the pleasure of knowing quite a few of them used to meet monthly at Fran's Restaurant on College Street and just looking for job prospects. And then it became a monthly gathering, and then was born the Lunch and Learn. Before starting today's presentation, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it's been the traditional land of the Huron-Wendat, the Senecas, and the Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. A quick housekeeping item: at the end of today's presentation, we have time for formal Q&A. Should you have any questions for Professor Hattrick-Simpers, please submit them using the Q&A button at the bottom of your Zoom screen. For the individual who submitted questions during the registration period, thank you for pursuing your curiosities and sharing your insightful questions with us. We have shared your questions with Professor Hattrick-Simpers before today's presentation, and we'll continue to share any new questions asked during the presentation at the end of the session. Now, without further ado, it gives me such great pleasure to introduce our MC and chair of the School Lunch and Learn program, Laurie Hevola. Laurie is not only an Electrical 65 grad, but he's also one of our most dedicated and engaged members of our alumni community. Laurie has been chairing the School Lunch and Learn program for several years and continues to generously dedicate his time to maintaining our Lunch and Learn's long-standing traditions. And with that, please join me in welcoming Laurie, who will introduce our speaker for today's event.
Thank you, Sonia, for your very, very warm introduction. It is my pleasure to welcome our guest speaker, Professor Jason Hattrick-Simpers. Today, he will be discussing best practices for the implementation of artificial intelligence techniques in the field of material science, the challenges and successes of his research, and why he believes that robots can help us learn to better trust AI. He is a professor at the Department of Material Science and Engineering here at the University of Toronto and a research scientist at CanMet Materials. He graduated with a Bachelor of Science degree in mathematics and also a Bachelor of Science degree in physics from Rowan University. And his doctorate is in material science and engineering from the University of Maryland. Prior to joining U of T, Professor Hattrick-Simpers was a staff scientist at the National Institute of Standards and Technology, otherwise known as NIST, in Gaithersburg, Maryland, where he co-developed tools for discovering novel corrosion resistance of alloys, developed active learning approaches to guide the film, and additive manufacturing alloy studies, and developed tools and best practices to enable trust in AI within the materials science community. And now, without further ado, please join me in welcoming Professor Jason Hattrick-Simpers.
Okay, just a quick thumbs up confirming that you all can see my slides. Laurie?
Yes, everything? We can.
Oh, fantastic. Thank you all for the introduction. Thank you all for taking this time from your days to come and listen to me speak. I appreciate your time, and I'm hoping that we can have a wonderful conversation. And so, look, I'm Jay. It's really great to meet you all. I'm really looking forward to this discussion. Let me set my timer. Perfect. I'm an experimentalist, right? I'm a newbie to this field of AI and of so-called large data sets. And so I just wanted to take this opportunity to have an open discussion with you all about my views on how we can, where is the field sit now? Where are the green fields that we should be moving to? And how in moving in those directions do we come to trust and depend on AI to help guide our experiments? So, clicker's not working. Try again. Perfect. All right. Bottom line up front, right? Let's just make this clear. AI in the physical sciences, it's already ubiquitous. And there are an increasingly larger number of people who are using AI-controlled robots inside of their labs doing science right now, including in my own labs. That's awesome. And it feels like the future, and it's already the past. The future is this opportunity to combine physical insights, expert heuristics, and tacit knowledge with our AIs to enable robots to do things that we couldn't dream of now. For instance, think creatively about problems, help us, guide us, generating new hypotheses. We're going to talk about a couple of the road bumps that are the bumps in the road that are coming along, including the fact that labeled data, which is the grits upon which the AI mill turns, it's hard. And ground truth is more nuanced when you really get down to it than we sometimes expect. And archival data can be hard to get. And even when you can finally get it, it's difficult to trust. And as a community, it's great. We have these robots and we're going to talk about optimization a fair amount, but I really hope that we can get back to doing science, right? Moving away from just rote optimization and correlation and move back into the world of causation, because we do science to gain understanding. And then finally, I want to wrap with the idea that there is the very real possibility, in fact, it's very real possibility because we're building it now, that there is going to be in the near future an internet science of things where interconnected robots and computational tools and data sets are all talking to one another around the world. So let's jump into it. First, quick introduction to my group here at the University of Toronto. We're the Autonomous Discovery of Alloys Lab, or Autodial. Our focus is in the discovery of new materials using what's so-called high-throughput experimental techniques, the development of autonomous research agents, robots that do science, and using these tools and our own analytical thinking and reevaluation of models as they come out of the robots to engender trust among the community in AI. And, scientifically, that's what we're interested in. But from a broader standpoint, what we really want to do is we want to empower citizen science. We want to help develop and disseminate open science platforms, open data, and open code so that anybody who has the interest in participating in the scientific process has an opportunity to do so and contribute to the community. All right, so why are we talking about AI at all? This is almost redundant at this point. Wow. If you check the news, you can't go a moment without seeing another one of these incredibly head-spinning AI breakthroughs. Even on my slide, self-driving cars, real-time translation, and AIs that beat best in the world video gamers at their own games. These are even a couple of years old, but they're on the news and we're constantly seeing how AI is going to help to improve our world. It's accessible, right? You can go online, you can download Weka or sklearn and then jump onto Coursera or Stack Overflow. And in a couple of hours, you could be building your first AI models on your own data sets. And more scientific data is available. There are things like the MGI, the Materials Data Facility, MatBench. Places are making their data open and freely available so that you can interact with it, build models, and build new understanding from what they've already done. And it's rosy, but we have to keep in mind that materials and physical science in general are not sort of what you would consider the usual AI use case. When we think about Facebook or Google and image segmentation or image recognition, we're talking about big data. We're talking about 10 to the 8 examples of people's cats. Whereas in the physical sciences, in particular material science, data is expensive. And so we have few of them and they're sparsely distributed in whatever our feature space is. The prediction tasks are different, right? I want to know that that's a cat. Is that a plastic bag? In material science, we want to find these same type of patterns, but we're also interested in the outliers because that's often where the new science and the new engineering concepts are. Domain knowledge is not necessarily applicable in traditional AI, whereas we increasingly want our AIs within the community to be aware of the rules and the heuristics that we have. And we're always, always, always worried about the uncertainty of our models and more worried about how do we interpret the results from the model. But this is not an obstacle, this is an opportunity. So let's take this opportunity. I'm a material scientist by training, and whether you're looking at energy conversion because you want to turn CO2 into something useful, you want more efficient turbines, you want to additively manufacture or 3D print your Iron Man robot fully functional, or if you're just interested in saving lives and saving money through looking at corrosion resistant materials, we need new materials yesterday. And the palette or the dimensional space that we're looking at when we talk about needing new materials is massive. I mean, we have, for our ingredients, we have the periodic table. And if we consider only 30 non-toxic earth-friendly elements, and we only consider combinations of 3 of them, there's about 4,000 ternaries and roughly 4 million different combinations of these alloys that we'd have to consider. And to be clear, in modern state-of-the-art alloys, you're talking generally 5+ intentional elements plus impurities. But correct ingredients does not a risotto make, right? It's not just having the elements together and putting them, mixing them, and boom, you have a brand new state-of-the-art alloy. It also comes down to how you process it, just as though you can't make risotto with just rice and water. You have to understand how to make the material, how to heat it, how to cool it. If you need multiple different annealing temperatures. And so this is an example here. Quasi-crystals won a Nobel Prize in 2011 for Dan Shechtman. He discovered them in the 80s using a melt spinner, basically 10⁻⁷ centigrade per second cooling rate. We recently found quasi-crystals naturally occurring in meteorites in Russia, where these things were cooled roughly at 10⁻⁻12 centigrade per second. So that's a 20 order of magnitude difference in the way that these materials are processed. So we need new materials, but there's a lot of different materials we could make and a lot of different ways we could process them. And so as a graduate student, we worked in this sort of space of high throughput experimentation where you could take spray gun A and spray gun B, tilt them off center from one another, and then spray them and get these wonderful composition gradients of all the different possible combinations of A and B. And that allowed us to rapidly look at these huge ternary phase diagrams with hundreds of different measurements of different properties. And we could do what used to take people months, years, or maybe never, we could do in a week or in 2 weeks. And that was fantastic. But what you realize quickly is the hypothesis engine, or the method of generating statistical correlations between the data points to help predict what should be interesting next, quickly becomes an obstacle, and that becomes rate limiting. So what did we do as a community? We talked to our friends that were doing AI, and we said, hey, look, we've got all of this observational data, all these data points that we've taken over all these years. Let's turn those into training sets. And we have some knowledge. We understand why these materials behave this way, why they have these properties. let's take these physiochemical theories and let's turn these into attributes. We can then train models on these to make predictions. Will it be a metallic glass? Will it have interesting properties? And then we promised, as quick as you can turn the crank, we can validate these. We can run sample by sample, hundreds and thousands of compositions in a month. Those new discoveries, and the wonderful part about AI is it doesn't matter if it's right or wrong to the AI. If it was right, fantastic, we found something new, move on. If it was wrong, okay. The model learns from that, applies that lesson uniformly across the rest of the data set, and then makes new predictions that are better than they were before. And then you even have this opportunity where a scientist can sit down with these new discoveries, these new materials, identify new correlations, new causal rules, create new knowledge, and then generate these new theories that make the models better. And so we demonstrated this a number of years ago. And if high throughput experimentation increased the rate at which we can make materials by 100 times, we put another 200 times on top of that. And we were able to identify new metallic glasses 200 times faster than could have been done prior to the integration of AI. And that is awesome. But we couldn't science fast enough, right? So this is a recent project with NIST, UMD, SLAC, Northwestern. We're looking at thermoelectric materials, and we were making the materials at UMD and NIST, characterizing them for their figure of merit, thermoelectric, their ability to turn heat into energy, and then characterizing their structure at Stanford. This was a really great project, but about a couple weeks in, I realized something. Our model validation latency was that we could look at 4 ternary systems per month pre-COVID. And as a HDE person, that's fantastic. That's way faster than anyone could have done in your sort of traditional material science space. But those AI folk, they were training, every time we gave them new data, they'd train their models and then they'd make a bunch of predictions. And then 24 hours after we gave them our data, they'd have a whole bunch of new predictions for us to look at within a day. And so as the experimentalist, I'm now the rate limiting step. I used to be so fast, and now I'm the slowest kid in school. And so we quickly realized that if you want to keep pace with AI lead generation, you need to have scalable synthesis and characterization tools. And so a couple of years ago, this is a burgeoning field, this field of autonomous material science or autonomous science. A couple of years ago at the University of Pennsylvania, a bunch of us from Air Force Research Lab, UPenn, and NIST, and all of our best friends came, and we had a little nerd party about autonomous science. And, you know, what does autonomous material science mean? It means that a human and an AI sit down and initialize a set of experiments, define objectives, specify constraints, and provide the prior knowledge we talked about in the previous slide. You then hand off that information and the objectives to the AI and the robot, which then plans what experiment to do, makes predictions, decides between exploration and exploitation, makes decisions, and then pushes experiments, new samples to be made, new characterizations to be done, to a robot that performs those sets of experiments, performs those simulations, hands off the data to yet another AI, which is now responsible for extracting and representing knowledge and interpreting and trying to explain what it's observing, and then pushing that back to the plan stage so that you can continue this virtuous loop of new material, what is its properties, is it as good as we thought it was, probably not, could it be better, yes, and continue until finally you reach your objective function and you get to conclude. Right? You've achieved your objective. You're reporting new knowledge gained, and you can update this sort of outward facing data repository. And again, this sounds like science fiction, but this is the robot I built at my lab in NIST. And it was responsible for doing exactly these tasks. Let's find a new corrosion resistant alloy. How do we do it? Well, we use a Gaussian process model. We identify which composition to deposit. It makes the alloy, goes to a spot in the wafer, makes the alloy. It then characterizes the alloy's corrosion resistance properties, updates the model, and continues, again, this virtuous cycle of continually improving. And the things that you're able to do with these types of tools is just amazing, right? You're able to, so when you think about AI, you often think about, oh, well, I need 1 billion data points to even get started. In this instance, for this particular type of model, Gaussian process regression, we start with only a handful of data points. These points here, out of the possibly 1,000 that we could sample. So start with 4 points. And then the model makes a prediction about what's the next most informative point. And really all we're looking for are the set of compositions that minimize our slope and minimize our corrosion current. This guy and this guy over here. Whoop. Why won't that work? There we go. And so in this particular instance, what we found was that we didn't even need to measure every of the 1,000 points. We didn't need to measure hundreds of points. We could let our robot make the decision about what measurement to make. And within 20 or 30 points, it had found what are the so-called Pareto optimal compositions. And there was no point in measuring anything else. Again, it's like science fiction, but it's happening and it's really cool. And it allows us, right? These robots aren't replacing us as scientists. It allows us to reevaluate what science means to us and what is actual science activity. And so if we think about, scientific concept as being sort of things that are incremental changes versus radical changes, and our application goals in terms of incremental versus radical change. Application goal, radical change. Electric cars don't need to drive 30 miles per hour in order to be interesting. They can be fast and they can be cool. Scientific concept, radical change. What if I use Scotch tape on this piece of charcoal? Do you think I could get one layer of graphite off? Most of our autonomous systems are working currently in this sort of incremental space. As scientists, we get to continue to enjoy this sort of radical change, outside the box thinking, hypothesis generation and generalization of results. And with time, as AIs continue to improve, we might even be able to get them to the point where they can begin to engage, or at least inform and help us to identify potential outside of the box types scientific inquiries. But we're also scientists because we want to understand, right? So if you think about AI on this axis of explainable versus interpretable, an explainable model is something where you can generate a model of data and you put another model onto it in order to try to get some sort of insight from it. And so your convolutional neural networks or deep learning sit pretty far on this less interpretable axis. More common things like random forests and neural networks get a little bit grayer. But as scientists, to predict is nice. If I can have a material that could predict a brand, if I have a model that could predict a material with superior properties, that's nice. That's patentable. That's interesting. But it's not extensible. It's not generalizable. What I want is to understand. I want a model that is interpretable, right? I want something that allows me to make a new insight beyond just that material is interesting and starts to say, like, here is the relationship between type 1 and type 2 superconductors. Great. And so a couple of years ago, a bunch of us at NIST and at NSF sat down and sort of thought to ourselves, what are the opportunities that these AIs and these autonomous systems enable us to sort of explore? And so right off the top, one thinks about scientific AI. Again, an artificial intelligence algorithm that is somehow informed by our physical understanding of the world, and it is not just correlatory, not just making correlations. The development of cyber-physical infrastructure, I want to sit in my basement in Etobicoke, and I want to write an AI that controls a robot at Brookhaven National Lab. I want that. How do we gain trust in AI? And how do we develop the workforce who understands these tools and knows how to ask the critical questions that enable them to identify when a prediction is fallacious? Through that discussion, we identified a series of paths forward, including collaboration across MSc, computer science, sociology, statistics, applied statistics, the development and continued refinement of these autonomous research platforms, the generation and dissemination of reference data, the building up of consortia, such as the Acceleration Consortium here at the University of Toronto, and again, the development and dissemination of best practices within the field. And all told, we sort of identified 28 community actions that intersect these opportunities and paths forward. So what is a scientific AI? Well, let's talk about scientific sitting versus AI in a very simple toy problem. Let's consider that I have some set of data that I'm taking, say grain size as a function of yield strength. And I could take a Gaussian process regression model and I could fit this data exquisitely within the realm of which I've taken data. I'm in an interpolative mode. And then once I get outside of the data, the GP knows that it's not doing so well, there's no data. And so its uncertainty increases, which is, by the way, represented by this color bar. And the model toddles off to who knows where. So we say AI models extrapolate poorly. Conversely, if I know something about the physics of this model, I can set a really simple inverse square root law. It's a Hall-Petch relationship. And I can fit that data, particularly in this interpolative area, just as well. However, I know and I have confidence that if I continue to take data, that Hall-Petch model is still going to do just as well at fitting the model that data that it's never seen as it did before. Whereas our AI model is very flexible, but extrapolates poorly. And so our physical model not only does a better job of fitting, but it provides us now physical insight, an ability to understand why. Unfortunately, physical models are brittle. And so if I continue, for instance, to decrease the grain size, eventually, if all I had was the Hall-Petch relationship to describe yield strength versus grain size, the model breaks. Here now is where AI shines, because as long as I have more data, my model can always be updated. Whereas my Hall-Petch model, if that's the only thing I had, I'm out of luck now. And so a scientific AI, for instance, would do something like perform Bayesian inference on these types of coefficients and then add a Gaussian process on top of that as sort of a slot factor for when the physical model breaks down. And I have examples we can go through in the QA if we have time. But all of this presupposes that we have data. And let's talk about data, because data is surprisingly a thorny issue. So if we consider the research space of data, we already know that there is domain bias, and there's a large portion of that space that is unexplored, right? Because we're afraid, because we want to look at data, we want to look at samples that other people have had some success with, and we're afraid to venture out into the greenfields. What even makes it out into the literature is an even more biased data set, whereby people drop questionable or inexplicable points, and you just get this subset of a subset. Moreover, errors make their way out of our labs and into our papers, and if those are being encoded into our AI as training data, then where are we? We're with a model that is going to be making poor performance and have poor performance and make bad predictions. Moreover, this actual data set, we oftentimes throw away the failures. There's this great paper by Josh Schreier at Fordham University from a couple of years ago, where they demonstrated that data bias in our sort of extent literature, where we get rid of failures, works to our detriment. In fact, a machine learning algorithm or an AI can learn just as much from looking at failed experiments and using those to identify new potential reactions. And that's even if you can get to the data, because unfortunately, we live in a world that's entirely digital, except our data, which is in textbooks like Landau and Bornstein, and your graduate student has to go into that textbook, open the figure, go with a slide rule to figure out where each one of those data points are labeled, and then enter them into a database. And so how do we make this data, at least this blue data, open and available for the world? There's this concept in science called the FAIR principle. Data should be findable, accessible, and interoperable and reusable. And the idea here is that findable and accessible, why don't I put my data, particularly for things that I've published, on a website where people can have access to it? This requires resources and time, and that's another issue entirely. And to make it interoperable and reusable, why don't we convene groups of experts and have them sit down and say, look, this is the experiment that you are all doing. How do you ensure that we have the appropriate metadata and data required to ensure reproducibility of your work, so that if you've deposited this particular sample, that group can do the same, and vice versa, so that we're all building off of one another. And this is possible, and it's something the community has realized and we're pushing forward with, but you understand that each discipline has very different needs and requirements when it comes to reproducibility. And so there are wonderful organizations like schema.org that sort of seek to create broader ontologies. But how do we label the data? And that's the funny thing, because if I look at this rock here, right, you come to realize that there are different flavors of ground truth, right? If I look at this rock here, pick it up off of the ground, I believe as a scientist in ground truth. I believe in causality. There are a set of rules that determine this rock's state of matter, and there are a set of rules that determine its interaction with the world around it, with electromagnetic radiation and temperature. I also accept that this is unknowable. The actual ground truth is unknowable. It's too complicated for me to understand. And so as scientists, we live in the world of tilde ground truth. I take my rock, I throw some electrons on it, I get a selected area diffraction pattern, and I determine a tilde state using things like rules for interactions, Bragg's law, idealizations of the state of the rock, and rules for how the atoms inside of it, that there are atoms, even get to arrange with themselves. And so from this selected area diffraction pattern and my tilde ground truth is that this is a crystalline material. Your AI doesn't understand about tilde ground truth. Everything you tell it, your labels are considered to be infallible. They might have some uncertainty, but they're correct. And there are also hidden assumptions underneath this that your data need to obey in order for most of the models that we use to properly work, not the least of which being that they're independent and identically distributed. And so that final ground truth is based off of user bias. And so what I think this rock is depends upon whether I'm a 2-time Nobel Prize winner or a 1-time Nobel Prize winner. And so if I'm Paulus Lining or Linus Pauling, I think that this is a twinned crystal. If I'm Dan Sheckman, consequently from NIST, I think that it's a brand new state of matter that I've discovered in its quasi-crystals. But if we don't capture that disagreement, how then do we promulgate this forward? There's also this issue about reproducibility in the sciences. these are some great articles, and they're not recent articles. They're not recent quotes. They're from 95 and 2003. I love this. The 16-page refereed learned journal paper is no longer adequate as the standard for dissemination of scientific knowledge. When you think about where the field is right now, people are actively pouring millions of dollars, tens of millions of dollars, into using natural language processing algorithms to pull out the information from these PDFs that we have stored on all of these Elsevier's and other journal publications, trying to pull that information back out that the graduate student had in their head at the time that they were writing the paper. And so this is a hobby horse of my own, but the PDF is dead. Let's pretend for a moment that we don't live in the 16th century anymore, that we're living in the 21st century. How on earth are we still using 21st century technology to reproduce 16th century state-of-the-art technology, right? And so we have tools. We could be doing this today. Many of your students, your children, your colleagues are using Python. They're writing code and they're using what's called a Jupyter notebook. You can use this to generate your sort of standard traditional scientific formatted paper, but there's a catch, right? You click on that little button and all of a sudden you're down into having the capability of working with the code. And so instead of just being a passive reader of some learned paper, you're an active participant. You have the opportunity to challenge the author's suggestions, to challenge their attestations, their suppositions, and to build on what they've already generated. This is here. This is now, but it's not now. This isn't what our present looks like. This is what our future has to look like. And I'm just about out of time, but I just want to tell you all that this is all happening here in Canada and at the University of Toronto. We have institutions like the Acceleration Consortium, which bring together scientists from multiple different departments, from FACE, from arts and science, from all over Canada, from national labs, bringing them together in this sort of generalized goal of creating these new autonomously driven AI-enhanced platforms that help us to identify and solve society's largest materials or chemistry-related problems. And the group is only expanding. And we're building capabilities. So this is the new NRCan Canby Center for Accelerated Materials Discovery and Innovation being built right now in Mississauga. This lab is meant to be the focal points of federal academic and industrial research inside of these autonomous systems. And it's meant to be the sort of international collaboration. So the goal is 1/3 of the folks from NRC, 1/3 of the folks from NRCan, and 1/3 of the folks out external collaborators, both from Germany, through CCMAC, through University of Toronto, University of British Columbia, bringing all of these wonderfully brilliant people that I get to interact with every day into the same building, pushing these technologies forward. And the dream is, again, I'm sitting in my basement in Etobicoke on my laptop, pulling data from some central data store, generating models about what I think should be the most next interesting materials to do, pushing those forward to a resource manager, which is then saying, okay, well, we got time on this particular instrument, let's run your experiment. Or maybe we're pushing it to some high performance computing center because it makes better sense to run a simulation. Then we pull this data back in, reformat it into the data structure that we've been using, and then push that to you. I don't have to imagine that. We're already doing pieces of that, right? This past summer, I was literally sitting in my basement in Etobicoke, writing in AI, driving a synchrotron experiment at Brookhaven National Lab, right? These things are already starting to be demonstrated, but let's not just demonstrate them, let's build them out. Let's dream big. Let's start the process of creating the Internet of Science things. Why don't we create an interconnected network of these autonomous systems with a shared data science framework so that we could actually maybe solve some of these massive scientific problems like getting the CO2 out of the air in a more rapid and maybe internationally harmonious way. And let's go a step further. Part of my lab's focus is on the development of open data science platforms that come with a manageable budget, because it is unfortunately the case that not every researcher in the world is at a tier 1 institution. Many really brilliant folks are off at other institutions and don't have access to the same amount of support that we have. I would love to be able to develop a platform that would cost less than $5,000 that we could distribute to any lab in the world, in developing countries, in poorer areas in the States. We have many areas, particularly along the East Coast of South Carolina, and get these people to have the opportunity to engage in the scientific process, and not just engage in a boxed up and let's look at that, the magnet floats on the superconductor way, but actually meaningfully add data or compute or new models to a large pool of knowledge that continues to push society forward. Again, it was bottom line up front, now it's bottom line down below. As I've said, AI in the physical science, it's here. It was here a couple of years ago. Having that AI control scientific robots, likewise, is here. The step forward, the leap forward that we can take is in now developing our own scientifically informed AIs, really getting our hands on how to structure data and share data freely among our collaborators and likewise with the world. Realizing that we're doing science to gain understanding, not just to optimize a material, and use this as a moment to reevaluate how we use AI. And imagine for a moment that Internet of Science things, starting here in Canada, eventually making an impact that changes the entire world. So you don't just have to imagine it. Please come and join us. We have multiple openings at the moment. If you're interested in water purification, working with Professor Werber, Professor Lee, and myself on a brand new program with Suez Water and Technology. If you're interested in medical applications, working with Professor Matsumaro and myself, looking at using images to help diagnose, basically taking pictures of children's heads to help diagnose rare and very debilitating diseases. And I'd like to acknowledge my key collaborators and funding agents over the year during my time in the States, and am very much looking forward to a very open question and answer. Thank you.
Thank you, Jason. While you were in your basement in Etobicoke, I am in my basement in the other end of town in Don Mills, and I get to lead off asking the questions. We have a number of questions that were posted online and some that were submitted in advance. I'll begin first with the online questions. The first one came up very early in your presentation and was from an anonymous attendee who said, "I'm loving the potential for AI to continue help with research. How will you take into account that we don't really understand how AI learns and applies this knowledge? And will this take away from the reliability and validity from that research if we don't understand how AI came up with the knowledge?"
That's a fantastic question. I would say that, let me just quickly back my slides up. I would say that when we're talking about, whoops, I'm out of time. I would say that when we're talking about things like neural networks, I tend to agree with you. They have very low explainability, and so it can be challenging to understand how they function and how they are making their assumptions, how they're making their conclusions. For my group, we try to stay we hew much closer to looking at interpretable models, or even models like random forest, where we have the opportunity to ask the model, what about my data set was important? Which of my features was particularly pertinent for making this prediction? Do I believe that that is even a feature of interest? Which of the data points was most impactful on making a particular prediction? And so in this sense, we actually do have an opportunity to sort of see how the AI is making its decisions. Gaussian process regression is similar in that sense. We try to hew personally on this interpretable, very explainable end. But there are also really interesting work coming out of the computer science community right now in terms of trying to understand how a deep learning AI makes its particular decision. And I'm not personally in that space. There's a great book called The Alignment Problem that goes over those things in pretty good detail. I think there's hope, but for myself, for the time being, I hew towards interpretable.
Thank you. Speaking of neural networks, the next question comes from my Lunch and Learn colleague, Jim Courtney, who asks, does any of your work incorporate the neural networks developed by Professor Jeffrey Hinton?
I would have said 3 months ago, no. Again, just because my own personal bias towards interpretable and explainable models. But I'm recently really interested in what are called variational autoencoders, which are based off of neural networks, sort of an unsupervised neural network technique that people are applying to a lot of the types of problems that I'm interested in, spectroscopy and diffraction. And they seem interesting enough to sort of start to dive down. So probably more and more in the future.
The next question comes from Jacqueline McCoon, who asks, how do you see standards such as those from the International Standards Organization, or ISO, affecting this field, both AI and AI/MSE?
Okay, well, coming from the National Institute of Standards and Technology, this was something we thought about quite a bit. And so sort of broadly, what I see are less standards and more dissemination of best practices. And so right now in the field, basically everywhere, banking, physical sciences, sociology, eco, AI is a little bit of the Wild West, where folks are employing models because it's relatively straightforward to do so, making predictions, but not understanding issues, for instance, with bias in their data sets, not able to sort of adequately understand the impacts of things like data set imbalance and classification tasks. And so I see a great opportunity for NIST and ISO to sort of push forward best practices for how to recognize these types of problems and to address them, so that at least we, an unbalanced data set doesn't mean you can't make models. But when you consider what the confusion matrix looks like, you have to start to consider the minority phase as your primary measure of how effective your particular algorithm is.
Thank you. The next question is from Zachary Garipi, who asks, how are you using AI for the RO postdoc position?
Great question. So at the current moment, we have an individual who's in the process of applying these types of image segmentation techniques and some more advanced statistical techniques to be able to effectively quantify the microstructure of the membranes used for reverse osmosis. And so what you can understand is that as a graduate student, I make a membrane, I take a scanning electron microscopy image of it, it's got some pore structure. I have to quantify what volume fraction of that is the pore, and maybe get some rough information about the sizes of the pores. And I leave a lot of meat on the bone. How are the pores interconnected? Is there necking of the pores? Are they expanding? Do I have different regions? And so there's a lot of information that we could be getting out of those images that we are currently not. And so that is one example. And then the other example is material synthesis, just like baking a risotto, is a sort of iterative process where we understand what are our processing parameters, but not necessarily where in that search space we're able to optimize not just the material's microstructure, but also its eventual properties, in this case, its ability to purify water. And so they'll be generating predictive models based off of synthesis to sort of match to property and microstructure.
Thank you. The next question comes from Ahmed Khan. Thanks for a very interesting talk. I have two questions for you. Perhaps you could take them one by one. The first, in terms of the example with noisy data, if we already have a good knowledge of the underlying physical phenomenon, why would we use machine learning in the first place?
If you have physics, then you don't need machine learning, is my personal take. As long as you're reasonably convinced that you have a fully described model over the range of materials properties you're interested in. Now let me back off of that a little bit. I'm working on a project right now with a student where we're interested in performing inference, where we're basically doing inference on diffraction patterns. And in there, we've got a really strong forward model for understanding what phases are present inside of the diffraction pattern, but it's difficult to get quantitative information about, you know, the amount of ordering that's present, the relative grain sizes, the presence or non-presence of stress, compressive versus, the relative presence of microstrain within the sample. And so in that particular instance, even though we have a good physical model, we have an infinitely degenerate space of potential solutions. And so what the AI is helping us to do is to identify what that degenerate space looks like, and then help us to identify inside of that, where are the sort of closer to global minimums.
The next question, what about areas like condensed matter physics, where new forms of matter are being found by exploiting the incredibly arcane and bizarre rules of quantum mechanics? Do you think that knowledge-assisted AI or unassisted AI could be useful in these areas?
Yes. Answer is yes. And I know that Professor Alana Sporoguzik in the chemistry department is currently working 100% in this space. Outside of my normal range of expertise, and so other than to say, yeah, it's definitely happening, I don't have much to add in terms of detail.
Thank you. Next question, fairly short, from Rishi Kumar. How should we distinguish interesting outliers from noise or errors?
Oh man, that is the best question ever. And it's really challenging, right? Identifying outliers. So to my mind, at least initially, you want to check with, I'm sorry, we're going to get a little technical. To my mind, the way that I would start off with that type of a question is, first and foremost, I'd ask, is my model unduly influenced? So I'd use the concept of influential instances as a method of identifying whether that particular data point is pulling or pushing my model in one direction or another. Then I'd start to concern myself with the feature space itself and where does that potential outlier or noise point sit inside of my feature space. If everything sort of sits and is sitting on a reasonably smooth function, except for that one particular data point, I start to think to myself either outlier or something very special. I then start to ask, are there replicates? Have people taken additional measurement points? If it's sufficiently of interest, for instance, the figure of merit is fantastic and I would win a Nobel Prize for having discovered that material, I might consider making it again.
Thank you. We are nearing the top of the hour, so one last question from Farhim Ahmed, who asks, great presentation. With high throughput experimentation in finding the properties of different compositions, you are producing alloys at different cooling rates. How do you take this into account when performing it? Furthermore, how do you ensure that the different elements have alloyed? I'm curious about this, as making alloys from elemental constituents with additive manufacturing was my MSc, Master of Applied Science Research.
Great question. First answer is I get to cheat for that second question. I'm typically using physical vapor deposition techniques. And so I'm actually getting atomic mixing of the elements at the substrate at the point of contact. And so I don't have to worry about, for instance, if I was melting something and I have like coring, right? So for that particular case, I'm never worried about the different elements alloying. Now, could they phase segregate into multiple phases? Sure, but I'm typically using some sort of structural characterization, diffraction, or XFs to try to suss that out. Different cooling rates. That's also a great question. And so there are a number of ways that you can do this. First of all, if you're performing the experiment at nominally the same composition, same structure, same processing envelope, you can assume that the cooling rates are similar to within an order of magnitude. And so for that particular sprint, you have materials that have been deposited at relatively uniform processing rates. As you push through and do additional experiments where you're cooking the materials and cooling them, or maybe in your case, you're moving the laser over the top of your sample with different hatch and different laser speed, or maybe even different focus, then those become features inside of your description of your material. They are correlated to the eventual microstructure and phase segregation that you observe in that material, and thus would be very informative features. And you would hope somewhere down the line, someone would be able to make a really good finite element model where you could actually, or not finite element, phase field model, where you could actually even interrogate the microstructure and encompass that inside of your feature set. So briefly, take it into account by knowing that you're changing it and making sure that you're quantifying it. And I'm cheating.
Thank you for those closing remarks and answering all of the questions, virtually except for one. Most of them came up at the end of your presentation, and we had a flood of them. We still had a couple more left, which unfortunately time will not allow us to address. I would like to take this time to thank you for all of the questions, for handling them from our audience. Before we close, obviously we want to thank Professor Jason Hattrick-Simpers for being with us today. Thank you for such an informative and fascinating presentation on artificial intelligence. To everyone who joined us here today, we invite you to share your feedback on the Skule Lunch and Learn series, which, as Sonia pointed out, has been going on for many, many years. A link to the online survey is being made in the chat function at the bottom of your screen and will be shared with all of you by email after this event. Also, a link to the presentation will be shared with all who registered guests early next week. Skule Lunch and Learn events are traditionally hosted on the second Wednesday of each month. Our next Skule Lunch and Learn event will be on Wednesday, May 11th, featuring Professor Marian Touchy. However, this specific Lunch and Learn will be slightly different from the Lunch and Learn presentations we have all become accustomed to over the last 2 years. How? We are excited to share with you that the next Lunch and Learn on May 11th will be offering not only a virtual option, but an in-person option once again at the Faculty Club. That date will be 26 months since the last time we were able to meet in person at the Faculty Club. And my understanding is the Faculty Club, in keeping with the university's requirements, is that masking will be required when entering the Faculty Club to help put your mind at ease. For more information about our next Lunch and Learn presentation, please visit our engineering website. In closing, I would also like to thank and acknowledge TD Insurance and Manulife, who are both sponsors of School Lunch and Learn through U of T's Pillar Sponsorship Program. If you are interested in learning more about School Lunch and Learn series, please contact the alumni office by email at events@engineering.utoronto.ca. Finally, in closing, I would like to thank all of you for joining us for today's presentation and hereby adjourn today's session of School Lunch and Learn. Have a fantastic rest of your day, and I look forward to seeing you in person next month. Thank you and goodbye.